Okay. I think already somebody has started recording, or okay. So in today's lecture, we will be discussing about the experimental validation of our numerical simulations or preclinical analysis, as I was telling you. So as discussed, that validation and verification are two important procedures that need to be undertaken in order to prove the validity of your results, predicted results. So in many cases, we do a lot of numerical simulation, and thereby we predict numerical results, and the results can only be considered as relevant or feasible if and only if the results are validated or verified. Okay. So what has been very nicely presented in a paper by Viceconti group, I would like to sort of share with you. Now, what is the difference between validation and verification? Okay. Now, validation, listen very carefully, that validation is about solving the right equation or solving the correct equation. So the correct equations means you have to write the equations, the governing equations of the system correctly. That is very basic. Okay. That you have to be careful that you are writing, you are solving the correct equations or the right equations. Okay. In comparison, verification is about solving the equations correctly. Okay. Here it is a matter of how you are solving the equations correctly. It's about the solution procedure of the equations. Whether there is repeatability, whether there is, convergence of results. You change some parameters here and there, number of elements. Say number of elements was 100, you increase the number of elements to 200 or 300. How is the result converging? That is verification. Okay. So the basic difference between verification and validation is validation is you have to write the governing equations correctly. If you don't write the governing equations correctly, everything is wrong. Whereas verification is about solving the equations correctly. Okay. So the term verification is commonly used to indicate the process ensuring that the numerical model accurately predicts the results of the theoretical model it is based on. Okay. So verification is commonly used to indicate the process ensuring that the numerical model accurately predicts the results of the theoretical model it is based on. So it is a model is verified by its numerical accuracy. Okay. On the contrary, the term validation indicates that the process ensures that the numerical model accurately predicted the physical phenomenon it was designed to replicate. Okay. So basically, you have to write the governing equation correctly. That means you are trying to accurately predict the physical phenomenon it is designed to replicate. So often the validation is carried out actually by experimental methods, and these experimental methods should actually replicate or mimic a certain numerical model, or vice versa. A numerical model should actually replicate the experiment what you are performing, and then you can actually have one-to-one comparison of the predicted results versus the measured results. So that is purely validation, right? So let us go through the slide. The finite element analysis has been extensively used to test and validate clinical hypotheses, and in particular preclinical evaluation of orthopedic implants. Okay, this we have learned over series of lectures how powerful is the results of a finite element analysis, provided it is validated or verified. And therefore, the accuracy of the predicted stresses and strain, or whatever you may like to predict, bone remodeling, other parameters, other variables, depend on the quality of representation of the FE models compared to the actual condition. This is extremely important. The accuracy of the predicted results. Therefore, the predicted results are always questioned. Hence, an assessment of the validity of the predictions is required before the FE model can be further used for clinically relevant investigations. Now, there are several techniques, as you know. You have come across strain gauge technique, I think, where we actually glue strain gauges directly on the surface of measurement so that we can get a local measurement, local response of the strain due to an applied load. Okay, so in this case, you can see a natural femur which is sort of fixed with some fixation and then loaded in a machine. So we have glued strain gauges. We have also used strain rosettes. Strain rosettes is a set of strain gauges which is oriented along a certain predefined orientation, of course. So there are 60-degree gauges, 90-degree gauges. So those things are there in a set of. It is basically a set of strain gauges together. It is called strain rosette. Okay. And we can actually get hold of different kinds of strains out of these measurements, which we can further compare with the predicted strains of finite element model. So experimental measurements using strain gauge states. Yeah.
Sorry to disturb, sir. Are you presenting slides because I'm not able to see them?
Yeah. Yeah, of course I'm presenting slides. Can
anyone confirm that I'm not able to see them? If everyone
No, sir, the slides are invisible.
Slides are not visible?
No, sir.
Oh my God. How can it be? You should have told me. Just a moment. Is it visible now?
Yes, sir.
So did you see this slide? Number 2?
No, sir, nothing.
Okay. So let me start from number 2 again. Just a moment. Hello? Can you see the slides?
Yes, sir.
Okay. Now let us go quickly back to second slide. The finite element analysis have been extensively used to test and validate different types of clinical hypotheses, and in particular, preclinical evaluation of implant designs and performance. Okay, that you have already studied extensively in this course, isn't it? Hello?
Yes, sir.
Yeah. Now, a lot of predicted results, evaluation, everything is dependent on the accuracy of the predicted stresses and strain. Basically the accuracy of the predictors depend on the quality of representation of the FE models as compared to the actual condition. Okay. This is when we say accuracy of the FE model or the accuracy of the predicted stresses and strain. So basically accuracy and the quality of the FE model are the two important things as compared to the actual situation. This is always questionable and debated. Therefore, an assessment of the validity of the FE predictions is required before the FE model can be further used for clinically relevant investigations. Okay, for clinical investigation. So we have to be always very careful that the results are clinically relevant. Otherwise, it makes no sense to perform all this detailed calculation and complex calculation on different kinds of phenomena. Hello, can you see?
Sir, you lost your connection, I think, in between.
Yeah, can you see the slide?
Yes, sir, now we can see.
Yeah. Yes, something is really going wrong.
Last class also couldn't take place.
Okay. Yeah, let me quickly finish this, otherwise it's a problem. So you know the difference between strain gauge and strain rosette? Students?
Yes,
Hello?
sir.
Yeah, so you have seen it. You have done some testing, I hope. So strain rosette is a set of strain gauges fixed, or oriented along particular directions. So you have different strain rosettes also fixed. Here you can see on the pelvic bone. Here we have strain gauges fixed on the natural femur, and thereafter the natural femur has been machined to put, the resurfacing implant. So experimental measurements using strain gauge technique has often been employed to validate FE models. You will get a host of papers where they have used this. Strain gauge measurements actually yield discrete data and a local data. The strain gauge measurements rather a very local data, which is an average of the real strains occurring underneath the gauge. Okay, this is very important. Okay, what it is about. What does the strain gauge response actually indicate? It is pretty discrete and it is pretty local, an average of the real strains occurring only under the gauge. Moreover, local surface preparation, instrumentation connected to the gauge and the temperature changes can actually affect strain measurement. This you already should know as a mechanical engineer regarding strain gauge measurements. Okay, so local surface preparation is very important. Instrumentation and the temperature changes, if any, If it is a major temperature change, of course, it will affect the strain measurement. Now we have done some pretty smart, experimental validation. As you can see, with strain gauges, not strain rosettes in this case, directly strain gauge measurements in-house. This is an in-house fabricated loading mechanism, biaxial loading mechanism, which would represent rather the loading of the femur in as compared to the actual condition. Okay, if you apply a load in the vertical direction, it can actually, this whole mechanism can actually distribute the load along two other directions as well. Okay. So here you can see the strain gauge is fixed on or glued on the surface of the artificial femur, as well as we have also used the LVDTs. So that is linear variable differential transducers. So this is basically the LVDTs displacements. So they actually measured very small relative displacement between the implant and the bone or implant cement. So you can actually, here you can see from the back side, it is measuring between the stem, the relative displacement between the stem and the bone. So one is, this is a LVDT3, and here LVDT1 and LVDT2 are measuring also the relative displacement between the implant and the bone. So just a little technical description with drawing regarding this in-house designed and fabricated loading mechanism. So you have roller bearings along two different directions, and then a vertical displacement on the top can actually translate into orthogonal displacement on the two other directions. And there is this socket, which is representing the acetabular socket, and the head of the femur actually comes in contact with the socket here. So you can see this employed for the load transfer mechanism. So you have intact femur, you have implanted femur, both loaded in mechanical testing machine. So when we actually compare, now we compare the results. So you have FE strains at particular locations compared with measured strains. And you can see that each symbol actually indicates strain gauge output for different load cases. Okay, so different loading has been applied, so the response has been measured and predicted, and so each symbol actually represents the strain gauge output. Output one can be numerical, other can be measured, so the output or response is plotted here, and you can see how nicely this is agreeing. Sort of, there is a pretty strong linear relationship between the FE predicted results and measured results, both in the case of intact femur and resurfaced femur. This is basically the load versus the strain curve. If we increase the load from 200, 400, 600, this is about one body weight, and this is twice, near about one body weight. This is about twice the body weight. Okay. Resurfaced femur. This is an interesting curve. You can see strain comparison between the natural and resurfaced femur. So if you compare the natural, number 2, it is here, the curve in loading. What is resurfaced 2? You can see that the strain response has reduced to a great extent. So this is basically the difference, which indicate that there is strain shielding in case of resurfaced femur. Consider natural 8 gauge 8 response of natural here and resurfaced femur, same location is here. So this is the basically the difference in strain due to implantation. It has reduced, the strain response is reduced. Now this is measured versus FE micromotion. So as I was telling you that it was measuring the displacement. So you can see here that LVDT2 is giving pretty good response, pretty high response as compared to the other two. So LVDT2 is here, this direction. Okay, so there is, movement along the LVDT2 as compared to LVDT1 and 3, because you can see pretty clearly that LVDT1, is very, very low response. So that means the movement along the medial lateral direction is very less, but the movement along the other orthogonal directions, and LVDT3 is interesting here, that the implant is moving relative, the implant stem, the resurfacing stem is moving relative to the surrounding bone. So there is some comparison plotted here as well. We have published this paper in Journal of Biomechanics, and if you are interested, you can also look into that in the detailed results. But this is just to show you that how we can extract data when we are doing some experimental measurement. Now, there are certain distinct disadvantages of the strain gauge technique, as I had already discussed with you, that these are localized measurements, and since the geometry is irregular and there is material inhomogeneity or heterogeneity, this together with irregular geometry and material heterogeneity, the combined effect can actually result in a large variation of stress strain across the structure. Okay. So if there is sharp gradient in stress strain field, it is unlikely to be captured in discrete experimental measurements such as strain gauge technique. Okay, so because it is very local, and the strain gauges are glued to the surface, and it is basically measuring the strain just below, very restricted to the local area of the strain. So it may not be able to capture the sharp gradient in stress strain field that may occur in certain regions of the bone, particularly where there is complexity in geometry or irregularity in the geometry. Okay. Therefore, continuous field strain data, full field strain data would be of benefit, such as what is predicted by a finite element analysis. Okay. So finite element analysis actually predicts a distribution over the whole structure. So something similar to that distribution would be beneficial. This is just a comparison. Displacement sensors, strain gauges, it's basically collecting data as a single point. Imagine if the structure is 3D, imagine a 3D setup. So we require more comprehensive analysis, not just a local data. Therefore, we actually need full field data rich experience. Okay, we need to experience. I'm trying to move into a little bit more into the DIC technique, the digital image correlation technique, how it is evolving. Okay, so we measure and visualize entire structure response, including 3D displacement and strain gradients. Okay, and this is also applicable for complex materials with complex geometries. Okay, here you can see your hand, your total palm with the fingers. And it is, I hope you are exposed to DIC technique, students?
No, sir.
You don't know what is the DIC technique? It was not taught in the class, in the strength of materials lab?
No, sir.
Okay, so basically you can see here that the surface or the measurement is conducted in such a way that you first paint the specimen with, apply a white paint, okay, and then let it dry, and then you spray black speckle pattern, okay, black speckle pattern, randomized speckle pattern, and then with cameras you can, and of course software transformation, you can actually track the movement of this black speckle pattern before and after loading. Okay, that is the basic theory. So you can see here that how this femur, is loaded in a testing machine, and it is actually the strain fields all over the femur. Wherever there is high strain, low strain, medium strain, full field analysis can be obtained using the cameras. You can see the camera here on the top, the light, white light, and the two camera, high resolution camera, which is tracking the movement of the speckle. You can see the black speckles here, background is white, and then you have to basically generate these black speckles with, on the surface of the measurement. We did that. Here you can see the specimen, a pelvic bone specimen with white paint, and the camera, one camera, two camera. Of course, there is some light, and we have the white paint over which we can actually generate the black speckle pattern. So DIC is a non-contact optical metrology or measurement technique that measures full field surface deformations on practically any material subjected to a driving force. Okay, so you have a pelvic bone, you have a femur bone as well. So we conducted experiments on both. And here you have the same two cameras as we had used it here. Working principle, the white light source, there's the camera, and then it's connected to the computer. This is the specimen. So basically in the specimen we have the black, we are trying to monitor the displacement of the black speckle patterns before and after loading. So they are trying to focus on an area of interest. So this is image before deformation, and this is image after deformation, the image that is being captured by the camera. Okay. So there is displacement, the position of the subset before deformation, and this is the area matched with the subset. So basically they are measuring deformation or displacement. So matching the subset before and after deformation. So this is what the program does. The correlating subsets, the function used to match undeformed to deformed subset is basically, this is a little bit of theory. which has been included here. So they try to minimize the error. So it's very clearly explained. So this is the undeformed pixel gray value, and then pixel gray value after deformation. Okay. Now speckle pattern has some influence on the results, on the DIC results. So we have observed that generating an adequate quality of speckle pattern is important. Otherwise, you don't get the results, very nice results of the correlation between the measured and the predicted data. So black on white or white on black is required so that you have contrast, because the camera needs contrast to locate these speckles. So always it is, it is easier when we have a black speckle on white background. So carbon black speckle on white painted bone surface was generated. So displacement of the speckle pattern was recorded by 2 cameras, digital cameras, and VIC 3D software. That was the software that is used for DIC. It was used to correlate the strain fields in the selected region, as you can see here. Now, image showing poor speckle pattern should not be repetitive. Low contrast is not desirable. We desire high contrast. Repetitive nature should not be there. So it has to be randomized. And the anisotropy, if you look into the VIC 3D testing guide correlations, and if you Google it, you will find it straight away. And you see the basic following a pattern is not important. Okay. So it should be more randomized. Now this is image showing good speckle pattern. Earlier was image showing poor speckle pattern. Okay. Non-repetitive, isotropic, high contrast requirements. Okay. Same in all directions. Okay. Not direction specific, which is here, poor speckle. The more the densities, it will take more the isotropic nature, but it has to be randomized, non-repetitive and isotropic and high contrast. So the specimen is pretty standard. You can see here, these are all specimen that I have shown you. Then we have implanted it, and then finally we have applied these speckles. We have generated very nice speckle here, as you can see. So by using the manual toothbrush, if we flick, we dip the toothbrush into a black paint, and then we flick it to generate this very nice speckle pattern. Okay, so this is all done by us, not taken from any manual. This is our specimens that we have generated in the lab. Okay, this is what is desired. Now we have dual camera and the specimen, and of course there is fixture to hold the specimen. And I have explained to you that what is there inside this loading mechanism, and this is the modular femoral head of the implant that was being used. So we have natural, intact testing done and an implanted testing done. So this is what is actually results that has been published in Journal of Engineering in Medicine, 2015, 6 years ago, on measurement on intact femur. I have shown you measurement on pelvic bone, but this is on intact femur, intact and implanted both. So in a region, you can have a full field distribution. So you have the FE predicted values, you have the DIC measurement directly available for comparison. So if you do the regression analysis, you get very high. You can also actually extract discrete values of DIC measurements at different regions. So we have compared the response, DIC response as well as the FE response at comparable regions, exactly similar locations. And this is what you get with a very high correlation coefficient of 0.926 and very low standard error of 26 microstrain. Okay, so obviously you can say that the FE predictions are valid. This was, I had shown you earlier, this was from the pelvic bone measurement. You can now have a look. This is from earlier slides as well. So this is the area of interest where we are actually undertaking the comparison between, on the right side you have the FE analysis, FE predicted results. On the left side you have the DIC measurements. And this is the correlation between the two. Intact implanted. Earlier one was also intact implanted. So between DIC and FE predicted. So this is DIC measured and FE predicted. This is strain rosette. So we have also used the strain rosette for measurement. So we are comparing strain rosette measurements with the FE predicted. So it's a two-way validation. So everything is validated. DIC validated, strain gauge measurements validated, FE predicted, results validated. Here also I've shown you earlier the three displacement LDS, the displacement sensors, 1, 2, 3, along three orthogonal directions. We tried to measure the implant bone micromotion or the relative displacement. So it shows pretty much similar trends between the FE predicted results and the actual measurement using LDS. This is in fact a sheep bone, fresh sheep bone from a butcher. We had tried to do the FE measurement and strain gauges response on fresh specimen of animal bone. So this is ovine bone, sheep. You can see this was DIC measured. It's pretty difficult because it's fresh bone. So, but we still tried to see what is really happening. This is first principle, second principle. And again, the other side, first principle, second principle. Posterior, anterior, both we have measured. A little bit of anterolateral, then lateral. Different locations we have compared. So now comes the regression analysis that we have done between rosette. So we have done some rosette measurement of principal strains because rosettes give you directly the principal strains. Okay, and this is the DIC measurements, and you see, very few data towards higher up in the loading. More data towards the lower side of the strain range. Okay. So we have high compressive strains, as you can see here. So the compressive zone here, compressive strains are higher as compared to low tensile strains. So this is basically what comes out of the strain measurements, as well as using Rosette data or DIC data. But still, we get quite high primarily because this data is, one is too high and the other data points are concentrated towards a very low range of strain. So obviously we'll get very high correlation coefficient, but that is not truly reflecting the scatter. So the conclusions are: results demonstrated good corroboration between DIC and established strain gauge techniques on fresh ovine bone samples. This data supports the validity of the DIC technique to obtain full field strain data on real bone specimens. So DIC can be used on real bone specimens quite effectively. And DIC technique can be effectively used for biomechanical analysis of bone and preclinical investigation on implanted bone structure, subject to careful specimen preparation. Okay, so this is very, very important, as I had shown you in the previous slide. And I thank you all for listening. Okay. Any questions, please? Hello? Hello?
Yes, we are audible.
Sir, if there is